Hello everyone, today I'm going to deliver another lecture on structural analysis by direct stiffness method for 2D frame or grid. Okay, the course content is include the we will find out the member stiffness for global axis system and assemble the stiffness matrix of local vector for 3D dimensional frame, and last one will show the math example of 3D frame or grid. Okay, so before going to the explain clarifying this, now I'll say why we are choosing the stiffness matrix method. So we know there are several uh, type of method we have used for analysis, such as one of them is virtual method. We just use for determinate structure and indeterminate structure both, but it is not used for the forces. uh, but it is used, we can find out the only for deflection purposes. We cannot find out the forces. On the other hand, we can see the unit load method is the same. It is as it is, we can use the determinate structure as well as the indeterminate structure, but we cannot find out the forces, but we can use for the deflection purposes, to find out the deflection purposes. And another one, we can see the force method. We cannot use the determinate structure for the force method, but however we can use the indeterminate structure for force method. In the same way, we can find out the force, and as well as we can use for the deflection. Okay, another one, we can see the moment distribution method, but we cannot use the moment distribution for the method for determinate structure. However, we can use the moment distribution method for determinate structure. But we can as well, and we can find out the force from the moment distribution method, but we cannot find out the deflection for using the moment distribution method. And last one, we can use the stiffness matrix method. So we can this method we can use for determinate structure and indeterminate structure. And we can find out the forces of any member, and we can also use for the we can find out the deflection also. So that's why we're now today we'll going to the stiffness, we will use the stiffness matrix method. So this is the stiffness method, direct stiffness matrix method. Now we're going to the deliver stiffness matrix for only for 3D grid and frame. So here is the stiffness matrix method. We can use the structural analysis direct stiffness method for 2D truss, 2D beam or frame. We can also use for 2D truss or 3D truss and 3D gridded frame. So today I will just today I will only deliver the lecture on 3D frame and grid. Okay, there are other several topics in related to direct stiffness method, from non-linear problems such as geometric non-linearity from beam and frame, and plastic analysis of beam and frame. And another was a direct stiffness method for structural dynamics. Okay, so only we will go to the 2D frame analysis for direct stiffness method. Direct stiffness method. Okay, let's start. So we can see here the three-dimensional frame. The three-dimensional frame have six unknown displacements such at each joint, such as deflection, which is U, P, and W, along with X, Y, and Z direction. So we can see deflection X direction in vertical direction and Z direction, and rotation ux, uy, and uz around x, y, and z direction. So therefore the size of the member stiffness is 12 into 12. So this will be huge, 12 into 2, which is the following from in the local axis. So you can see sx minus sx minus 1 iz minus 1 1 iz 1 y 1 txt mean torsion, and s means the stiffness. Okay, So in this way we can find out this 12 into 12 matrix. So the transformation matrix TM and the transformation matrix KMG global in the global access system are the complicated and not writing here. However, the method of applying boundary conditions solving this unknown displacement similar to the method of mention is ILR. Okay, so let us start. So we can see here. mm, Sorry, here. Okay, we can see here the another and two and 3D frame. We can see here the 3D frame or the member ABBC and BE. So this is the top view, so we can say this is the top view, and this is the isometric view. This is the isometric view, or you can say BC, BZ and CE. So CE member will be this position. Okay, so let's see here. These are the taken from here. This is the isometric and this is the top view. Okay, so how will now we'll assemble the equation. So we can see case 1, there are the three case 1, case 2 and case 3. So let's see case 1, which we are applying direct shear at B. So this is the B point. We can see B point, we are using the direction, that means we will use the upward force from left from bottom to up. So we are using S1 at point B. This is the point of B. S1 that means stiffness, we are just saying S1. Here is the another we can, if you want to, what does mean S1 means 12 EI by L cube. S2 means it will be half. If we say this is the 12 and this will be half, 12 EI by L cube, and it will be half, so which is 6 EI by L square, not L cube. Okay, in the same way S3 it will be 4 EI by L, and S4 will be half of 4, which is 2 EI by L. Okay, so when we applying the load in upward, this is the S1, and in the opposite direction will be S2. In the same as it is the vice versa will be S1, and same will be the opposite direction will be S2. For the rotation, for the deflection we are S1. On the rotation we can see it will be S2. This is the point of S2, and it will be opposite direction of S3. The same as S2 is opposite direction, but here is another extra we have to memorize. This will be S4, so you must be keep in mind. So if you format this is the S1, so what will be value? This value will be 12 EI by L cube, this value, and S2 will be 6 EL by L cube. So this is the short form we have been taking here. Okay, let's start here. From here we can see the top view and isometric view is given here. Now case 1, we are just applying the vertical load in upward. So what will be happen? So we can see in B1, see it will be S1. S1 is upward, which is AB, this member AB, this member, and BC, and B and C, this member. So this two member will be upward, that's why we are applying upward, that's why it is a S1 and S1, and opposite direction is must be S2. When this is the S1 and this will be S1, as this is the opposite, and S2 these are the here, and it will be S2. So S1, as we have been using shear, that's why we are applying S1, and the S1 is opposite direction will be S2. This will be must be memorized. Okay, so these two member are gone. Now we are calculating the member BE. This is the member of BE, we can see here. Okay, so what will be happen in member BE? It will be also going in upward, as we have been using shear, not torsion or not rotation. so it will be it will be going upward k1. Why k1, why not s1? These are the just we are taking, we're just giving the name is k1. K1, the value will be, the formula will be same as it is, as we know here is k1 12 bi by 12 ei by h cube. So s1 and k1 are the same, s2 and k2 is the same, s3 s4. The change will be t1. T1, that means torsion, jg divided by l. T2 will be same, jg divided by l. We'll see when we'll use t1 and t2. Okay, so k1, the value will be k1 12 bi by 1. It's the same as it is s1. We just change the name as the as we have been saying, this is the be be length, be portion. Okay, so AB portion we have been seen, and PC portion we have been rename is s1, and that's why we are changing the name from B, which is k1. Okay, this is not an issue. The issue is we are using the shear in the point of B. So if the point of B is upward gone, then AB and BC, this is the AB and BC will be upward. That's why S1 and S1 will be upward, and the opposite direction will be S2. The same as it is, we are applying this at the point B. That's why the K1 will be upward and K2 will be the opposite direction. The same as it is, K1 is here, so K2 will be opposite direction, and K1 will be opposite, and K opposite will be K2. Okay, so what is the value of K1, K2, K3? Is nothing but it will be S1, S2, S3. So as we know, S1 is 12 pi by L cube, S2 will be 6 ei by L square, and S3 will be 4 ei by L, and S1 S4 will be 2 L by L. Okay, so this is the case 1. So let's see the second case. I'm just changing the color from log. Okay, the blue color. So case 2, we are using the case 2 rotation. This is the case 1 is shear. So the rotation, you must be keep in mind rotation at B. Now we are using the rotation at B, which is BC and BA. What will be happen? BC and BA U1. Okay, so BC and BA, we can see BA and BC. These are the member. So BA and BC. If we take the rotation is here. So here I'm just okay, sorry for okay, I'm just taking the sniping okay, so now we can see the case 2 is rotation at B, which is BC and BA. If we open this here, so you can see here okay, sorry for that. You can see here okay, with case 2 we have been seen here the case 2 with the rotation at B. This means that we have been taking the rotation at B. So what will be happen? BC with the, that means these are the BA, these are the member of BA. So we have been taking the rotation in anti-clockwise. The rotation will be always anti-clockwise. Okay, the rotation is, when the rotation is applied, then the value will be S2. And the same as it is, the S2 is opposite direction will be S3, and S2 is here, that's why it will be also S2 is here. And remember, when the rotation is 3, S3 is opposite of S2, but in the opposite direction will be S4. On the other hand, we have been seen there is a S1 and this is the S2, and this is also S1, but it was also S2, but in this case why this one? Because when we are using the shear calculation, when we are calculating the rotation, then it will be changed. It will be not S3, it will be S4 instead of an S3. Okay, in the same easy test, as we've been using the rotation at B point B, that's why we have been taking the rotation and upward, then it will be opposite direction will be S3. So we can say these are the opposite direction, okay, as they are the hostile. So this is the S2 and it will be opposite direction also S2, but when the S2 is applied, it will be S4, not S3. So remember it, in this point, the in this point where the apply in root torsion, sorry, where the apply is rotation, that will be S3. So we are applying S2. S2 is upward, so S2 is here. The S3 is when the applying in this point, this is the rotation point. The far point will be S4. The far point will be S4. So keep in mind this here. Every student are taking mistake for here. Uh, every student are gone to mistake in this point. Okay. Now we can see BE member. So this is the BE member. What will be happen? The BE member will be opposite of the torsion. So you've been seen this the torsion T1 and T2. What is the value of T1 T2? T1 T2 will be JG by L. So you can see here JG by L. It is the value of T1 T2. What is the value of JG? JG value is given and L is the length. L is the length. It will be very okay. In the same as case 3 we've been seen, I'm just changing color from okay, the red color. Case 3 is the rotation at BE. Now we're going to the we will apply the rotation the member of BE. What is the BE member? This is the BE member. So that means when we apply the rotation BE, the more the and the opposite member, we're just using the rotation of B. So this is the first we have been applying more rotation BE. So it will be K2 and opposite direction K3, and it is K2 and opposite direction. The far in the apply load far into will be K4. This is the K3 and this is the K4, because we are applying rotation at B. This is the point of B. This is the near point, that's why this K3 and the far into will be K4. Okay, we are applying this K2. Okay, it all the rotation will be anti-clockwise. And the others member, so as we are using rotation at B, that is the B. This is the BE member. The opposite member, that is AB and SE, will be torsion, which we can see the A point is torsion T1 and B point is T1 T1 T1. All the member will be torsion, because we are applying the rotation is here. That's why the opposite direction will be opposite member will be torsion. As same as we have been used the case 2, is we have been a rotation at B point BC and BA member, such as if I remember you that, so these are the rotational member. So torsion will be opposite member, that is BD. That's why the BE will be opposite. So you have to keep in mind. So if you miss this, then you cannot go ahead. So I'm just saying again, this is the isometric view. We have three cases. One is shear. We have been going the shear point SB. If we go on the shear point B, then S1 will be upward and opposite direction will be S2, and the far into will be S1 and it will be also far into S2, opposite direction. And the other member, which is BE, this is the BE member. BE member we are using K1 is upward and opposite direction will be K2. K1 is upward, downward, and K2 is opposite. When we go to the rotation at B, which is member of specifically BA and BC, that means this point we are taking the rotation in anti-clockwise, then opposite member will be torsion. So we are taking the rotation in this member and it will be torsion. Okay, so we are just taking the rotation is here, S2 and opposite is S3 and far into will be S4 and S2 is opposite. and this is the torsion. When we are taking the rotation at BE member, so keep in mind this is the BE member. Okay, this is the this is the B, this is the E. So if we are taking the rotation is here, then BE, AB and BC will be torsion, and this will be rotation. So that's why we have been taking the rotation is torsion is here, AB and BC, BA and BC, and rotation is here only BE. Okay, now we can see the all the formulas here, and now we can solve this question. The question is given here. If we go to here, sorry, is not given here. Okay, we have been seen all the AB is 5 feet and BC is 5 feet. So we have been completed here. Now we will go to the math example. Let's see the math example. The find the deflection, rotation, shear force and bending moment. Also draw the bending moment diagram. Okay, so let's see. We can see a member is given. This is the top view and this is the isometric view. Top view is AB is 5 feet and BC is 5 feet, and BE is 10 feet is divided by 5 feet by 5 feet. If we see the isometric view, so we can see here AB is also 5 feet and BC is also 5 feet and BE also 5 into 5 into 10 feet. Okay, all the data is given here. Okay, now we can see what will be happen. As we have been seen here, all the data is given here. Now we can calculate. Now first case we have been use the finite element fixed in moment. Fixed in moment, or what will be what is the fixed in moment? Fixed in moment is nothing but is given all the data as it is the point load. So what will be happen? WL by 12. So in this case we have been found by 12.5 and 12.5. Okay, so fixed in moment is gone. Now case is B1, that means shear 1. So we've been shear BY, that's why the shear 1. So we've been using shear 1 is here. So I'm just saying here the shear 1. We have been taking the shear 1, that's why is S1 and S1. The opposite direction will be S2 and S2. So this is the S1 and this will be also S1. This will be also S1. The opposite direction will be S2. Opposite direction will be S2. The same as it is from for this this member, we have been apply the K1, and the opposite direction will be K2, and K1 is here far end and K2 will be opposite direction. These are the our first case. Okay, now we can using the rotation. At case 3 we are rotation using this member, which is called BE member. We just using rotation, which is K2, and opposite direction will be K3. The K2 is far end, the opposite direction K2, and the opposite direction will be K4. So as we have been used this member only rotation, so this member will be rotation, and the opposite member will be torsion. This is the torsion T1, 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 T1. The same as case 4, which is we have been using the rotation as Z in the Z direction. So the rotation will be this member. Oh, sorry, I just changing color. This will be torsion member and this will be rotation member. So keep in mind, we have been using the theta x. This is the, we can see the theta x mean if I change the color for your better understanding. So I'm just changing color. When we use the theta x, that means x direction will be torsion. When you use theta z, then the z direction will be torsion. then what will be torsion. Torsion will be opposite direction, opposite axis, not direction, opposite axis. So keep in mind, we have been using the theta x, that means x direction we have been used torsion, and opposite axis will be, another axis will be rotation. Okay, so theta x, that means we have been using x axis torsion and z axis will be rotation. You have to must be memorize this. What is this? We have been used theta z, that means we are taking the torsion in z axis, and the perpendicular or other axis, which is called x axis, we are taking the rotation. It's the same as we have been theta z, so we are taking the torsion in this direction, and rotation will be this direction. As we have been seen, this is the given the axis. Okay, so we've been seeing here the S2 is upward. If we see here, S2 is upward and S3 is opposite direction. In the same way, S2 is downward, S2 is opposite direction. The far end S2 is opposite direction, and opposite direction will be S4. The far end S2 is the opposite direction of this S2, and S4 will be also opposite. And these are the torsion. Here is T1 and T2. We are just giving the name T1, T2. As we have been seeing, T1 is here, the length is given is 5 feet. On the other hand, these are length are not equal. We have been seeing this the length is 10. That's why we are just giving name T2. Okay. So now we've been finding here, and we use the apply all the formulas here. S1 12bi by L cube, S3 4ei by L, K1 12bi by L cube, K3 4ei by L, and TL means Jg by L. Jg is given in question here, 30 into 10 to the power 3 cube per feet square. Okay, so after getting all this value, we have S1 12bi by L cube, S2 6ei by L square, x3 these are the of half, so you have to keep in mind, and S4 4ei by L, there is no square root, and S4 equal to 12bi by L, so keep in mind this will be half of the 4. On T1 means TL by Jg, so these are the complex. So now we can see K is stiffness, we've been given 12bi by L cube. In same it is K2, it will be value of half of K1, it will be also square, and K3 4ei by L cube, and K4 will be half of the K3, which is 4, there will be 2, and T2 will be TL by Jg. In this way we have been getting all this value. After all this getting value, now we are taking the summation of f of y. So f of y, what does mean f of y? We are just taking another I'm just taking another sniping picture for your better understand. Okay, give me a second. Okay, we just gone here. Okay, we have been seen here fy, that means this fy, as I have been giving the value is fy, but in this case they are giving another name, so don't be panic. The same, these cases same, and this case and this case are same, this case and this case same, and this case is same. Okay, let's see. Here we have been seeing fy. we have been seen here fy value, all the value. Sorry, I'm just I should take this value. Okay, okay, now we can calculate the fy. How we will calculate the fy? We have been now we are saying here 5. I will get the 5. 5 is coming from the fixed moment. This is the case 1. We have been seeing this is the 5. At point B we are calculating this point B, and 2 S1 K1. What does mean? Why we get the 2 S1 K1? These are the 2 S1 and 1 K1 is found here. We are just taking the point B as we have been mentioned here, point B. That's why 2 S1 K1 as BY. This is the BY. So K2 theta x, this is the theta x, and this is the value of K2. So we are taking this is the K2, and we are not taking the torsion. Why? Because we are just calculating shear, which is Fy. That's why we are not taking any T1, T2. Okay, now we go to the theta z. This is the theta z. In the point B, if we go to the point B, then we have been found the S1, S2. Sorry, S2 will be upward, and another S2 is downward at point B, only point B. So we have been between S2 upward and S2 downward, and theta z. S2 will be cancelled out with 0, and we have been putting all these value and finding this equation. And the same as it is, if we calculate the mx, that means the x-axis will be torsion. You must be memorize this. When we calculate mx, then torsion will be x-axis and z-axis will be rotation. Say for mx, we have been found mx point B. So we are calculating point B. I'm just changing color. Okay, so mx, this is the point of B, mx. We are just calculating. Now we're taking the moment is 12.5, the fixed in case. So now we go to the bx point, which case 2. Case 2, what will be found? K2 into by. These are the K2. We have been found the BE member, and we have been gone to the theta case 3. Case 3 we have been found in the T1. This is the T1, this is the T1. 2 T1 we have been found here, and 1 K3. This is the K3 we have been found in here. K3 in theta x. And if we go to the member case 4, there is no such data. Why? Because we have been taking the moment x at B. That means x-axis will be torsion. So if we go to the, this is the x-axis, there is in this member there is no torsion. That's why this point are 0. Okay, and if we go to the z-axis will be rotation. So in this z-axis there is no rotation. That's why this is the 0. So you have to keep in mind when we calculate by, then we'll take in data of by member. This is the by or case 2 member. When we calculate theta x, we will calculate this member data. Okay, after finding this member data, we are just putting all this value and finding this equation. In the same way, we are calculating the mz. So now we are calculating the mz. So please keep attention. We are calculating moment of z-axis at point B. Okay, so first case we have been taking the moment is here. There is no moment. That's why 0. Fixed in moment, there is no fixed in moment. That's why 0. So now we will go to the case 2. This is the case 2. I'm just changing color. Okay, I'm just taking the red color. Okay, now we're taking the point by. That means this case. So by, as we have been taking moment at z, so z axis will be torsion. These are the axis will be torsion. Okay, there is no torsion, and x axis will be rotation. That means this will be rotation. So we have two rotation we've been seen here. One is S2, another one is S2. So S2 is clockwise and another S2 is anti-clockwise. So S2 clockwise and S2 anti-clockwise. Okay. So now we'll go to the another case. This is the case 2, which is theta z. Theta z mean theta z means this is the case 3. So we are taking the moment z at B. That means z axis will be torsion. So these are the z axis. There is no torsion. I have been seen K2, K3, K2, K3. That's why we could not use any data because there is no torsion. We are calculating the moment z, so it will be z axis torsion. Now we'll go to the x axis for rotation. This is the x axis in diagram, but there is no rotation, but there is a torsion, so we could not use any data. Why? Because we are calculating moment z axis at point B, so it will be torsion will be z axis and the rotation will be x axis. That's why this is the 0. Now we'll go to the another case, case 4. So in the same as we calculating moment z, so z axis will be torsion. So this is the z axis. We have been seeing the torsion is given here. So this is the torsion T2. These are the torsion T2. We have been writing here, and the rotation will be x-axis. These are the rotation. It will be x-axis. So rotation will be seen 2 S3. So these are the S3, and these are the S3. All are the anti-clockwise. That's why we have been multiplied 2 S into theta z. After putting this value, the 3 equation 1, 2, 3, putting and solving these 3 equation with this calculator, and finding this equation, which is by is found minus 0.75 10 to the power 3 feet, and theta x will be minus 0.269 radian, and theta z will be 0 radian. Okay, these are the what angle and deflection and rotation. I will show the shear force. I will calculate the shear force. The shear force at A. So if you calculate the shear force at A, these are the point of A. 0 minus S2 plus Py. So if we go to here, and we have been seen the 3 cases. This is the case 1, fixed in moment, case 2, and case 3, and case 4. So I will go to the first case for calculating here the FA, and there is no shear at point 1 at point A. That's why 0. And the point B, we have been going here. We have been seen one shear, which is S1. Sorry, here S2 is here, and it will be By. This is the By multiply with Py, and we'll go to the case 3, and at point 1 there is no shear, that's why it is 0. This is the 0, and we'll go to the last one. We have been found S2 is here, and it will be multiplied to the theta z. It is the theta z case. So all the point of A, we will take all the point when we calculate shear force at A. Okay, and finding this value. So let's see another point, which is B, which is AB. Okay, I'm just changing color here blue. So there is no share we've been seen here. There is no share. The second case we've been seen B1, which is S1. S S1 we've been we are seeing this is the S1 as we've been taking here. Another we're taking here. There is no. That's why it will be 0. And last one we've been seen here, the S2. This is the S2 and theta z. That's why we've been finding this shear force. In the same way we've been finding shear force at BC member. That means this BC member and all this member, putting all this data and finding here. Okay. And shear force at BE we've been finding here, and all the data after putting all this data and finding all these values here. Okay, now we calculate the bending moment. How we calculate bending moment at point A? Okay, let's see the bending moment at point A. There is no bending, this was 0, and we've been for case 2, the second page, we've been seeing the S2 is given here. S2 is founding S2 into By, and there is no data, that's why these are the 0. And last one we've been shown the S4. This is the S4. Okay. After putting the value in founding 16.81, and we can use the bending moment diagram at point B. We have been seeing the AB member. This is the bending point B. Okay. So we have been seeing there is no bending, that's why 0. And second picture, we can see here the second picture. We've been found S2 into By. These are the S2 and these are the By, and last we can see there is no S1 S2, sorry, S2 S4 S3, that's why it will be 0. And last one we've been seen S3. These are the S3 into theta z. It will be theta z, and finding this value and putting all this data for a bending moment B point BE, bending moment C, bending moment BE, and bending moment E point E, and finding all these data is here. Okay, so now we can see the torsion. How we calculate the torsion? Here is the torsion. Okay, so how we calculate the torsion? Torsion is nothing but, I will calculate the torsion. We can see torsion A. This is the torsion point of A. Just erasing this all that value. Now we calculate the torsion point A. Okay, torsion point A. First diagram there is no torsion at point A. 0. Second diagram there is no torsion at point A. That's why 0. Third diagram there is a torsion. So T1 into theta x. And last one there is no torsion at this point. That's why 0, and finding 1.78. In the same way, if we change the color for red AB member, these are there is no torsion. The first diagram. In the second diagram also no torsion. That's why 0 0. And third diagram we have been found a torsion, which is T1 into theta x. And fourth diagram there is no torsion at point B. That's why the 0, and finding minus 1.7. In this way we've been calculating all this data and finding all the torsion is here. Okay, so let's see another. Use the stiffness matrix methods to calculate the rotation at point C. This is the point of C for the grid shown in given EI modular ratio, maybe EI. Flexural rigidity is called flexural rigidity. EI is given here and JG is given here. Okay, so we've been seeing this portion are cantilever. That's why we can use WL square by 2, and which is found 50 kip feet. So after so 50 kip per feet we can use here, but we can erase this point, eliminate. We can eliminate this point. So now we can use the theta x. Theta x means these are the we have two direction is here. This is the x direction and this is the z direction, and y is vertical. So theta x, that means x direction will be torsion. So we are taking the torsion is x direction, and perpendicular member will be rotation. This is the perpendicular. We have been taking the rotation is here. After applying rotation, the member will be acting like this. And the theta z, that means the z direction will be torsion. These are the z direction. They will be applying all the torsion, and another direction will be rotation. So applying rotation, it will be acting like this. The fixed in moment is given here. Okay, so now we can see, now we can after applying here, we can see here z2, z3, s3, s2, s3, and t1 is given here, and this direction is t1, t2, t3, t4, and h1, h2 is given here. So after here we have been putting all this value as to 6 ei by l square. So z2 will be 6 ei by l square, h2 equal to also 6 ei by l square, and s3 equal to 4 ei by l, z3 4 ei by l, h3 8 ei by l, and t1 TL by JG, as we know JG by L. So JG by L is given. T1, as we have been known, the length is 10 feet, that's why divided by 10, and it will be JG by L. L is 5 feet, as we know T2. As if you see, this is the T2, so these are the length is given 5 feet. And another one is T2 JG by L. L is 15. How? As we have been T3, this is the length of the length is given is 15. So after putting this value, where this mx, what does mean? The x axis will be torsion and z axis will be rotation. You must be keep in mind, otherwise will be fail. So x is in the first diagram we have been taking here, we are taking mx, that means x axis will be torsion, that's why we have been taking t1. This is the t1x, and second we have been taking the rotation is here. There is direction rotation, it is taken s3, this is the s3, and z3 we have been also taken z3 x, this is the z3, this is the z3. So there is no x direction torsion, there is no x direction torsion, we are not taking from data here, and there is no rotation in z direction, that's why these data are 0, 0. Okay, after putting this value and finding this value, and in the same way as summation of moment z, that means the z direction will be torsion and x direction will be rotation. So you have to keep in mind. So after putting this value and finding this value, in the same as it is, we have been calculating the shear force, point C, and bending moment also, and torsion also. Okay. Now we see the another example. Use the stiffness matrix method to calculate the rotation at point C. This is the point of C, and for the grid is shown given, EI is given, and JG is given. So as these are the cantilever, we are just putting value 5 into 10, this is 50. It is the applied the bending moment is here, so it will be short form. After putting value, we are taking case 1, which is theta x, that means x direction will be torsion, this is the x direction torsion, and z direction will be rotation. And theta z, that means z direction will be torsion and x direction will be rotation, and this is the fixed in moment. After putting this value and finding all the value z3, s3, t1, and t3, and in the same way we can calculate the moment is here, is given as per as shown in previously and as here. Now we can see another example. Use the stiffness matrix to calculate the deflection rotation at point C. So these are the grid we have been seen here. These are the also we have been seeing the cantilever 5 into 10, which is 50. So 50 keep we have been applying is here at the moment as it is moment, and finding here case 1 which is particle shear, and theta z, that theta x mean x direction will be torsion and the z direction will be rotation, and theta z, that means z direction will be torsion and x direction will be rotation, and fixed in moment. After solving this equation and after putting the all the values here, s2 z3 and t1 jg by l, and z3 s3 t2, and finding all these below. And in this way we can calculate the fy, which is force, and it will be equation 1, and mc x direction, that means x direction will be torsion and z direction will be rotation, and mc z, that means z direction, z axis will be torsion, and axis will be rotation, and finding this value. After finding this value, solving this value and finding this equation, this value. Okay, and these are the another example we've been seeing here. Given this data from, we have been taking the FBC, and theta x, that means x direction is torsion and y direction is rotation, and theta z, what does the theta z means z direction is torsion and x direction we have been used the rotation, and this is the fixed moment. After solving this, then you will find the answer. Another example we've been seen here. I use the stiffness practice to calculate the deflection point G and F of the grid system. Given this loaded zone is the figure below, EI is given, and JG is given. So we've been seeing these are the diagram, and we have applied case 1, which is vertical, vertical direction. We've been using the shear, which is S1 and Z1, and case 2 have been seen here. This is the using S1 is here, Z1 is here, and S1 is here. Then case 3 is fixed in moment is here, and after putting all this value, we have been finding S1 Z1, and we have been taking summation of Fy, and finding this equation, and we are taking the summation of Fy F, and also finding another member, another equation. So okay, so you can see another example is given here. This is the member. After finding this member, we are just taking the summation of x, that means x axis will be torsion, this is the x axis, that's why torsion, and the perpendicular will be rotation. The same as we have been taking the theta z, that means z axis will be torsion, this is the z axis, we have been applying torsion, and axis will be rotation. The fixed in moment, after fixed in moment, calculating all this value and finding all the data. I think the lecture is ended. If you have any question, then let me know. Before I'm going to leave, I just saying again how to calculate, how to solve this problem. So at first there will be there is a grid. So I will find the value. So this is the general solution. The first one, case 1, which will be using shear. This is the shear at point B will be applied. So S1 will be upward direction and opposite will be S2. The same thing, we are just changing the name. The K1 will be upward and K2 will be opposite direction. Now we are taking the rotation at point B, that means BA and BC. What will be? So we are taking the rotation is here, B and BC, and opposite direction, and the other member will be torsion. The same thing, the rotation at B. So if we take the rotation of B, and the opposite direction will be torsion. Okay, after putting this value, so this is the member we've been taking here. We're just taking B shear is first case 1, we will take the fixed in moment, and second case is shear is upward at the point 1, and theta z, that means z axis will be torsion, sorry, theta x. So x axis will be torsion, and z axis will be rotation. So these are the important. When we apply theta z, that means z axis will be torsion, and the another direction which is x axis will be rotation. So you must be keep in mind. So after solving this equation, and we will finding all this value data and finding here how is summation of f of y and summation of m of x. This is the important. How we will calculate mx? That means x axis will be torsion. These are the very important. So we all the if x axis there is no torsion, so we cannot take this. This is the x axis is torsion. So we'll take this here. So there is no torsion is x axis, so we cannot take in data. So in this way we can take the torsion only in x axis. This is the x axis, and as mx, so rotation will be z axis. So rotation will be z axis. So rotation will be z axis. Rotation, there is a rotation k1 k2, so we'll take this from here. Rotation we have been taking from here z axis, so we'll take this here. So two rotation we can take here. Okay, so we can see here is a rotation we've been taking cat3, and there is no data from fixed last one. So that's why in this way we can taking all the data is here. I think we can understand. You can understand. If you have any question, then let me know. And this is the formula derivation, and this is the formula, and you have to must be keep in mind the formula. There is no other option for without formula. So formula you must be keep in mind. So I have been already learn you how to memorize the formula. Say for we are taking the deflection at this point, so it will be s1. S1 will be upward, so opposite direction of S1 it will be S2. So far into, what will be far in? Far into will be S1 will be in the opposite direction, and it will be opposite direction of S2. For theta or rotation, what will be happen? We just applying the theta in anti-clockwise. These are the anti-clockwise. That's why the S2 is downward. The opposite direction will be S2. But keep in mind, it's very important. For rotation, when you apply this point is S3, the far end will be S4, and then these are the S2. So if you calculate, memorize this and practice this, then you can understand easily. You just using put the formula, which is S1, which is we can see 12bi by L cube, and this is the half will be S2 is 6. We've been seeing writing here. This is the 12 by L cube, and S2 will be half. This is the 12, and it will be half. That means 6, and this is the cube, and this will be square. And what will be S3? S3 is nothing but 4ei by L, and S4 will be half. Will be 4 in half is 2, which is 2el by L. So you can justly keep in mind this anyway. I think you can understand and you can keep in mind. Thank you everyone. If you have connection, and we have been taking this in both from Professor Dr. Kibar Anam sir, and another was from Group. Thank you for your